reaction and rate constant. Okay, so the rate of a reaction mainly depends upon the concentration of reactant. This representation is known as rate law or rate equation or rate expression. Okay, so always decreasing the reactant concentration, increasing the product concentration, okay, with respect to time. Okay, so consider general reactions. A reactant react with B reactant produce C and D products. Okay, this A and B and C, D are stoichiometric coefficients. Okay, stoichiometric coefficients means this much amount of moles. Okay, so 1 mole of reactant react with 3 moles of reactant to produce. Okay, so that is stoichiometric coefficients means it's some amount of moles. Okay, so A, B, C, D are stoichiometric coefficients of a reactant and the product. Okay, so how can you write for this rate expression? Rate expression means nothing but rate law or rate equation. Okay, so rate proportional to, that is, it depends upon the concentration of reactants. What are the concentration of reactants? A reactant. So this sign, this square bracket, it represent, it is a concentration of A raised to the power x and the concentration of B raised to the power y. Okay, so what is this xy? Okay, so xy are exponents and it is experimental value. So this is the x plus y is order. Okay, so order we cannot determine by own, so it is get from experimental value. Okay, so that this case this xy is not, may or may not equal to this stoichiometric coefficients of AB reactant. Okay, because of this is we are getting from experimental value, from experimental only this value we can get. Okay, right. So rate equal to this proportionally we can write K. This K is represent rate constant. Okay, rate constant of the molar concentration of reactants. What are the reactants? Reactant A raised to the power x and reactant B raised to the power y. Okay, here, so for how can you write the differential rate equations? The smaller change of reactant concentration by at the time dt equal to rate constant K, reactant concentration of A raised to the power x and reactant concentration of B raised to the power y. Okay, so here, so because of this value xy is, it is a order. This order, it is not similar with this coefficient value. Here you see that the 2NO plus O2 gives 2NO2. 2NO2. Okay, so here how can you write rate equal to the constant K, the molar concentration of reactant, that is NO raised to the power 2 and the concentration of O2, okay, raised to 1. It is not here 1, we can assume that is a 1 molar concentration. Okay, so that is rate equal to 2 plus 1 3. Okay, here also 2 plus 1 3. Okay, so the order, it is similar with this case, it is similar with coefficients. Okay, no problem. But at the same time you see another one reactions I have to take. 2NH3 ammonia synthesis gives N2 plus 3H2. Okay, so here how do you write rate equal to K, rate constant of the concentration of reactant NH3, okay, raised to the power 2. It is not 2. This is, for this case it is wrong. Okay, because for the ammonia synthesis, this the rate constant value for NH3, reactant of NH3 rate constant value is K raised to the NH3, reactant, the ammonia, concentration of ammonia raised to the power 0. This is by the experimental. For this case, the experimental value of this order is, this is a 0 order reactions, not for this second order. For rate anything, the reactant concentration raised to the power 0, it represents 0 order. Raised to the power 1, it represents first order. 2 means it represents 2. Okay, so that always the rate constant, it is a experimental value. It does not depend on the concentration of the reactant. Okay, students, you keep it in your mind. Okay, so that here you see that rate constant equal to the rate of reaction when molar concentration of each reactant is taken as unity. Okay, for rate equal to rate constant of the molar concentration of reactant H2 and into molar concentration of reactant I2. Okay, 1 plus 1 here we can assume that is 2. Okay, K equal to the value, the order is 2. Okay, so rate constant K, it become unity. Okay, so students, you see rate expression or rate law or rate equations and rate constant. This is a one key point. Rate constant, it is a measure of the rate of the reactions, but it does not depend on the reactant concentration, only it depends on the order of the reaction. That's all. Today's session we are going to see two concepts, order of a reaction and molecularity of a reaction. Okay, so the order of a reaction is the sum of powers of the concentration of reactants in the rate law expression is called the order of that chemical reaction. Okay, so how do you write for rate law? Rate equal to rate constant into the sum up of concentration of reactants A power x and B power y. Okay, so this is a sum of and the concentration of reactant concentration of A and B, the raised to the power of exponents. Okay, this exponents x plus y equal to order. Okay, so this order, it is a experimental determined value. Okay, so it is any reactions it undergoing, it is based upon the experimental only we can get this order of the reactions. Okay, so for example, in our class, the total strength, all of them are not interested with studies. Some of them they are interested with studying, and others they interested with music playing, so etc. like that. So according to their ability for the reactions, it determined, that is the first zero order reactions, first order reactions and second order reactions, even the fraction order reactions also having. Okay, so order means it depends upon the that is the speed of the reactions. Okay, okay, so this is called order of the reactions. Okay, right. Next one, molecularity. So it is not students, you must keep it in your mind, this order value is not theoretical value, it is determined by experimental. Okay, right. Molecularity of reactions. Okay, so what do you mean molecularity of your reactions? Total number of reacting species. So it may be atoms or ions or molecules taking part in the elementary step is called molecularity of the reactions. Okay, so why here using elementary step? So because of so atoms or ions involved in reactants, it undergoing some reactions, it undergoing single step reactions, we can get the product. So that is elementary step. Okay, so some of the reactions it undergoing one step, two step, that is complex reactions. Okay, so complex reactions means it undergoing one or two steps. Okay, then only we can get the product. Okay, but in the molecularity only for applicable for elementary step reactions. Okay, right. So for example, number of reacting species, what is meaning by molecularity of your reactions? The number of reacting, total number of reacting species taking part in the chemical reactions. Okay, that is called molecularity of a reaction. Okay, so number of reacting species, suppose only one reactants it undergoing any chemical reactions, that is the molecularity that is 1. Okay, that reactions is called unimolecular reactions. Suppose two reacting species it undergoing reactions, chemical reactions, the molecularity is 2. Okay, so this reactions is called bimolecular reactions. Suppose more than 2, that is 3 or 4, it is a rare case. Okay, so the the molecules, atoms or ions it undergoing chemical reactions, this is the molecularity is 3, it's the reaction is termolecular or trimolecular. Okay, this and all rare case. Okay. Okay, so first the one means only one reactant, unimolecular reactions. Here the first unimolecular reactions, one reacting species is involved. For example, decomposition of ammonia. Okay, for ammonium nitrate is a single compound. This species it undergoing decomposition reactions. Students, you very well know that what do you mean decomposition reactions. Decomposition means splitted into 2 or 3. Okay, we can get the two products here, nitrogen dioxide and water. Okay, so this is one reacting species involved in the chemical reactions. Its molecularity is 1. Okay, so bimolecular reactions, two reacting species are involved, simultaneous collisions takes place. Okay, collisions means here, so the decomposition of hydrogen iodide, it gives hydrogen and iodine. Okay, here what's happening, suppose this is one container, this container we have to take a full hydrogen and iodine species, so iodine molecules. Okay, hydrogen and iodine, so these hydrogen and iodine collides means collisions takes place. Okay, so one to one, so approach each other. Okay, collisions ஆகிறதுனால இது என்ன நடக்கு அப்படின்னா easily, so here the simultaneous collisions between these two reacting species like hydrogen and iodine to produce a hydrogen plus iodine. Okay, so two products, hydrogen plus iodine. Okay, so this is two reacting species, that is called bimolecular reactions. Okay, right. So decomposition of hydrogen peroxide. Okay, hydrogen peroxide, actually this hydrogen peroxide decomposition reaction, it is a first order reactions. Okay, so first order means order, so rate equal to, listen, rate equal to rate constant K. So the reactant concentration raised to the power means it is a zero order. Okay, at the same time rate equal to K, reacting constant, the rate constant, the reacting concentration raised to the power means 1 means it is a first order. Okay, at the rate equal to rate constant, reactant concentration raised to the power 2 equal to second order. Okay, so this is for order. Raised to the power 0 means 0 order, and this is a expression in terms of concentration of reactant. Raised to the power 0, 0 order, raised to the power 1, first order, raised to the power 2, second order. Okay, some reactions are 0 order reactions, or first order or second order. Okay, here you see this decomposition of hydrogen peroxide, normally it is a first order reactions, it is a kind of first order reactions. Okay, so here hydrogen peroxide in aqueous medium in the presence of iodine, iodine is a catalyst in alkaline medium, so it produce water and oxygen. Okay, oxygen gas. Okay, but this reaction it undergoes two-step reactions. Okay, so two-step reactions means here for molecularity we have to consider the elementary reactions. Okay, elementary reactions means the overall reactions which step is controlled by, that is called slowest step and rate determining step. Okay, so that rate determining or slowest step we may consider the that is the rate determining step. Okay, right. So here these reactions, the first step, hydrogen peroxide react with this iodine catalyst, it produce water and this hypoiodite, IO minus. Okay, after that the second step, the same, the reactant H2O to hydrogen peroxide react with, this is the intermediate, this is what in the intermediate. Okay, so this intermediate react with this intermediate to produce H2O and I minus and O2. Okay, so for here this iodine and this iodine get cancelled, this iodide and this iodide can get cancelled. So the overall reaction is the hydrogen peroxide to produce water and oxygen gas. Okay, but the order is first, but which one is the slowest step? The first step is the slowest step, so that is the rate determining step. Okay, so this is the molecularity of reactions. Okay students, you keep it in your mind. So number of ions or atoms taking part in a chemical reaction, that is called molecularity. Suppose only one reacting species, first order, that is unimolecular, two reacting species, that is bimolecular, more than two means it is a somewhat complex reactions. So complex reactions means which step is controlled by the overall reactions, that is called slowest step or rate determining step. So that we have to consider the reaction. Okay, so molecularity of the rate determining step. Okay, right. Here also the same thing, it is a first order reactions, but it is the first the step is a slowest step, that is a rate determining step. Okay, right. So here students, one question will ask you, what is the difference between order and molecularity? Okay, so the order is the sum of powers of the concentration of the reactant in the rate law expression. Molecularity means total number of the atoms or ions taking part in a chemical reactions. Okay, and so it is only experimental value, but it is a theoretical value. How much number of ions or atoms taking part? So it is a theoretical value. So it is a order of reactions, it is a fraction order, zero order, first order, second order, and fractional order also there. But the molecularity of a reaction, it is a whole number. Okay, so 1 2 3 whole number. Okay, it is a number, whole number only. So the order of reaction can be zero, but the molecularity of a reaction cannot be zero or fractional. Okay, so these are the three key points you have to remember, that for the difference between order and molecularity. This one, two more question, that's all. Unit of rate constant. Okay, suppose we may consider the general reactions, a particular reactant, it gives the product. Okay, so for this case, how can you write the rate of the reactions? Okay, so rate always rate depends upon the concentration of the reactant with our product with respect to time. Okay, so here for this case, how can you write rate equal to rate constant of the concentration of reactant? Okay, right. So suppose rate equal to rate constant of the reactant concentration raised to the power 0, that is a zero order reaction. At the same time, rate equal to rate constant of reactant concentrations raised to the power of 1, that is a first order reactions. And rate equal to rate constant the reactant concentration raised to the power of 2, it is a second order reactions. Okay, right. So here you see here the rate, usually rate depends upon the concentration with respect to time. Okay, and so concentrations, how can you write the unit? Mole per liter. Okay, so time is we measure the time is second. Okay, or else how can you write mole per liter per second? Okay, this is for the rate. What is the unit? Mole per liter per second. Okay, right. So now we are going to find the unit of zero order and first order and second order. Okay, for zero order, so rate equal to the rate constant of the concentration of reactant raised to the power 0, that is the zero order reactions. We may consider that is a zero order reaction. Okay, for this case, rate, we already know that rate equal to concentration by with respect to time equal to K means that is a rate constant. Okay, so anything in your mathematical form, anything raised to the power 0, that it is a 1. Okay, so here you see that, so the rate equal to concentration by time, rate constant K. So anything raised to the power 0, 1, so the whole term only it is a, we may consider that is a 1. Okay, so K into 1. Okay, right. So here the concentrations, usually the unit of concentration is mole per liter, by the time per second, that is the time, equal to K. Okay, right. So for this case, rate equal to mole per liter per second. Okay, so this is for zero order reactions. Suppose in your exam point of view, so the rate constant value is given, ask you to what is the order, first order or second order or zero order. How can you find the order, particular order? Once you have to see in the unit, then you will find the particular order. Okay, right. Here I can write, I have written some example, 2.6 into 10 raised power 3 the mole per liter per second. So you see that the unit mole per liter per second, this is a unit for zero order. Okay, then it is the order of zero order. Okay, so like that you asked rate constant, given rate constant, and ask you to write first order, zero order. Okay, for this case it is a zero order because the unit. Okay, next first order. Okay, what is the first order? Rate equal to rate constant, the concentration of reactant raised to the power 1. Okay, so rate equal to mole per liter per second. Okay, so rate constant, and R is the concentration. Concentration means that is the unit is mole per liter. Okay, so here this mole per liter and this mole per liter get cancelled. So K equal to 1 by S. Okay, so then K equal to per second. Okay, so per second is the unit of first order reaction. Suppose in your exam point of view, 3.7 into 10 power minus 3 per second. So once you seen that per second, it is a unit for first order reaction. Okay, right. Then second order reactions. So rate equal to rate constant of the reactant concentration raised to the power 2. Okay, so rate equal to mole per liter per second equal to rate constant. The R, it is a unit for mole per liter the whole squared. Okay, because it is a power of 2, no, so that is power of 2. Okay, so here this mole per liter and here 2 mole per liter is there. Okay, so it is a square. Okay, 1 mole per liter and here also 1 mole per liter, it get cancelled. Okay, so here and this is get cancelled. Then how can you write? For rate constant K equal to 1 by mole per liter, this is second. Okay, right. So இது இங்கே கீழே வந்துரும்ல, கீழே வரும்போது 1 by mole per liter and second. Okay, then K equal to, so இது மேலே அப்படி போகிறப்ப mole inverse and இங்கே liter inverse இருக்கு, மேலே போகிறப்ப liter and here second inverse. Okay, so this is the unit for second order reaction. Okay, so students easily you can find once you have to see the unit, then you may consider this is a particular unit for mole per liter per second. It is a unit of zero order. Per second it is a unit of first order, and mole inverse, liter and second inverse, this is a unit of second order. That's all. Okay.